morning to everyone. We will start with the session, and the title of this session, the first one in the morning, is Phenolic Compounds, Recent Studies in Disease Prevention. Well, first, I would like to introduce to Dr. Visioli. I think everyone in phenolics knows Francesco Visioli. He's very known in the phenolics world. He's professor at Human Nutrition at the Department of Molecular Medicine in Padua, and also associate investigator at IMDEA-Food. And according to the Stanford ranking, he's the top Italian researcher in nutrition and dietetics. So go ahead, Francesco. Thank you.
Thank you. Good morning, everybody. And I would like to start by agradecer a la Diputación de Jaén por organizarlo todo y meter dinero además. Sobre todo al Comité Científico, Estefanía, a los organizadores, Elena, muchísimo, y Virginia, que es la que nos traslada, nos organiza el día a día. Entonces es un placer, cada vez es un placer estar en Andalucía en general y en Jaén en concreto. So today they asked me to speak about olive oil polyphenols. Olive oil polyphenols, why? So we know, we've been hearing these days olive oil use, preferential use of olive oil is associated with better health. So the question is why? No one knows why. Maybe it's because we eat more vegetables. Is it oleic acid? Probably not. Oleic acid has very minor effects on health. If you use oleic acid instead of saturated fatty acids, then it might be healthy, but it's not oleic acid per se. It's when you use it, when you replace other kinds of fatty acids. Is it because olive oil lowers cholesterol? No, not really. The effects of olive oil on cholesterol are very, very, very small. So people will love to say this, but it's not. And let me see if I can go back. I just published an editorial in the Journal of Nutrition accompanying a review, a big review of all the studies. The effects of olive oil on cholesterol are super small. And even if there was an effect, it does not really justify why olive oil is healthy. So let's see the latest results or the latest data on olive oil polyphenols. This is actually the first pharmacological use of olive oil. If you read the Bible, the Good Samaritan found a patient with a wound, infected wound, an inflamed wound. What did it do? It poured olive oil. Actually, it didn't really pour olive oil. At that time, there was no olive trees. There was oleaster. I think it's still found in Spain, and they find it Acebucha, I think it's called. And if you find it, I have a collaboration with a group in Algeria. If you find it, you can study it. So people still use oleaster, super high in polyphenols. Oleaster oil is super high in polyphenols. And so back then, the Good Samaritan used a very high polyphenol olive oil to do what? To treat a wound. That was probably the first pharmacological use of olive oil, extra virgin olive oil. Now we accelerate a little bit. So from 2,000 years ago, we moved to Jaén. And this is a bit of a history, because in 1993, my former mentor, Claudio Galli, and I became interested in this paper by the Greek group of Dimitrios Boscu. And they tested what? They tested the antioxidant actions of hydroxytyrosol. So, and they compared it with BHT. BHT is what? It's an antioxidant that we find everywhere, in fries, in cookies. They use it. But look at this, hydroxytyrosol is way more, let's see if it works. Yeah, it's way more potent than BHT. And back then, the oxidized LDL hypothesis was very popular. So this is the first publication ever where we used oligoprotein in 1994. So today we celebrate 30 years of research on olive oil and health. Before 1994, no one knew anything on olive oil and health. So 30 years, is it a lot? Is it not too much? I don't know. It took us 30 years to get to this point. But then we isolated hydroxytyrosol and we tested in vitro hydroxytyrosol on LDL oxidation. You oxidize them, they lose vitamin E. You add hydroxytyrosol, they don't lose vitamin E. So this is garbage now, okay? This is totally irrelevant. Unfortunately, antioxidants do not work in humans. The oxidized LDL hypothesis, maybe yes, probably no. So why is olive oil healthy? Again, what's very interesting and very important of olive oil and of extra virgin olive oil, it's very different from seed oils. It contains polyphenols. And two of them, hydroxytyrosol and oleuropenin, you find them only in extra virgin olive oil. Some people found them in wine, but it's a bit controversial. So what sets olive oil apart from other foods is the presence of hydroxytyrosol and oleuropenin. Okay? So coffee has more or less the same polyphenols of cocoa. Cocoa has more or less the same polyphenols of red wine, more or less. Okay? I know it's not like this, but and the two most important ones are these: hydroxytyrosol and oleocanthal. So again, how do they work? Why? Why is olive oil healthy? It's probably not because it's antioxidant. And even if it was antioxidant, you need to be very careful with antioxidants. So we were discussing with Edward this morning. Antioxidants, every time we give antioxidants to people, we increase mortality. So again, why? We've been studying this again for 30 years now, and this is the latest. You can read the papers and reviews. You can find them on the internet. I just wanted to show the latest evidence from my group. So maybe it's not a direct antioxidant activity. Maybe it's not a direct anti-inflammatory activity. Maybe it's epigenetics. Then I will tell you at the end, I will tell you what I think, what I personally think. This is a review we published on the nutriepigenetic actions of extra virgin olive oil. So forget removal of free radicals. That does not exist. So polyphenols do not remove free radicals in humans. Oh, we keep hearing this, newspapers, oh yes, drink red wine or drink coffee because they remove free radicals. That's BS. They do not. But maybe they work through DNA methylation. That's why people who use olive oil have less cancer, or cardioprotective effects, or neurodegeneration. So maybe one of the many actions of olive oil polyphenols compounds is that they modify epigenetic mechanisms, and very difficult to study. We wasted many years studying antioxidants, and now we need to go back and see anti-inflammatory activities, or see, for example, metabolites. So this is another paper we published with Alberto Davalos on this endothelial-derived molecule. See, there's a big difference. This molecule controls, look at this. This molecule controls replication in the intestine. So people who use olive oil lower colon cancer. Is it because they eat more vegetables? It could be. Is it because they use extra virgin olive oil? It could be. Or maybe the two of them. And we heard yesterday Miguel Angel saying, talking about metabolites. Very, very important, especially in obesity or in overweight. This is a paper we published a couple of years ago. The only thing I want to stress is this, is that we gave mice a diet, an obesogenic diet with lard, but in an amount that approximates human consumption. So lots of times you read papers when they take mice, they give them an enormous amount of something, for example, saturated fatty acids, and then they give them a compound they want to study, and boom, they see an effect. That's, when you go to humans, it's different. So this is what we saw, for example, body weight. So same amount of food consumption, body weight, slightly lower. We heard that yesterday from Professor Escric. People who use extra virgin olive oil, they do not gain so much weight as people who use, for example, butter or animal fat. Urinary polyphenols, circulating polyphenols, they increase. We can still measure them in plasma or in urine. And this is an interesting result, I think. So what we saw is a decrease in glutathione. And I published, maybe 20 years ago, 15 years ago, a paper where I used wastewater, in Spanish is alpecin, an extract, and if you give them to volunteers, you increase glutathione. So this is exactly the opposite, and I don't know why. Our hypothesis is that if you take polyphenols, you don't need glutathione. Okay, this is a bit extreme. But if you take polyphenols, your body does not need to produce as much glutathione as needed because you already have polyphenols and your redox pathways are already in optimal health, let's say. So we still don't know. This is our latest work, still unpublished. So take it as, yeah, probably yes, maybe no. We still need to write the paper. We went further. Is it extra virgin olive oil, or is it polyphenols from extra virgin olive oil? Is it fatty acids? So here we used, again, regular chow, soybean oil, 100% full of linoleic acid. Then we used lard, an obesogenic diet, so saturated fatty acid. Then we compare mice treated with extra virgin olive oil, polyphenols, squalene, vitamin E, and then we removed it. We removed the polyphenols from extra virgin olive oil, so same composition, same fatty acid composition, but no polyphenols. And finally, different fatty acid composition with the hazelnut oil, lots of tocopherols. So again, we compared polyphenols with vitamin E, with squalene, with fatty acids, in an amount that people use when they eat their regular meals in the Western world. Okay? And then we did, again, this is in preparation, we measured the polyphenols absorption. We wanted to know whether these mice took the diet. We measured body weight, and we measured glucose homeostasis. We heard that yesterday from Miguel Angel, who said, but why diabetics use extra virgin olive oil and they increase the glucose tolerance? Doesn't make sense. But it's true. If you look at the data, clinical data, it's true. So again, these are very, very preliminary data. Let me see if I can, yeah. We measured in the urine polyphenol level, all European went up, all European aglycon and all extroside, all polyphenols went up in the urine, in the extra virgin olive oil, not in the other ones, just a little bit in the polyphenol deprived olive oil. But this is also interesting, I think. So this is body weight. So these are the white ones are the normal chow, though of course they gain weight, but not too much. The other ones are mice on a obesogenic diet. And again, the green ones with extra virgin olive oil, they gain weight, of course, but less than the other ones. And anorexogenic effect that Edward was talking about yesterday. The mechanisms of action, yeah, we still don't know. But it's counterintuitive, or it doesn't make sense. You take fat, you do not gain weight, or you gain weight, but less than another kind of fat. It's 9 calories per gram, thermodynamics. But still, this is consistent. We saw that in mice, we saw it in humans. Is that because they eat less? Well, they start eating less at the beginning of the study because polyphenols are bitter. Then they get used to it, and then slowly, more or less, they eat like the other mice. So there's something in the brain, there's something that olive oil polyphenols do in the brain that makes you eat less. And this is the most interesting result, I think. This is why the paper, I like this paper, I like this investigation. Glucose tolerance. So look at the white ones are normal chow, so good glucose tolerance because it's a normal chow. The other ones are those with an obesogenic diet. Glucose tolerance, horrible. Plasma glucose increases, but not as much when you give them extra virgin olive oil with polyphenols. This is another way of looking at the data. The lowest, or the strongest effect on glucose tolerance is the one of the diet with extra virgin olive oil, with polyphenols. And then, of course, we did a bunch of, we're still crunching the data, so don't rely on this data too much. We did an ingenuity pathway analysis. Some genes went up, some genes went down, but this is the very preliminary conclusion of this part. The signaling pathways that went down are related with inflammation, oxidative stress, extracellular matrix, and the ones who went up, energy expenditure, peroxisome, mitochondrial function. Again, very preliminary data, but these are already, I'm already sure of what I'm saying. Well, extracellular matrix, I think it's interesting because if you look at the pre-med data, people do not die from stroke. And polyphenols, this is very poorly investigated, but polyphenols, for example, inhibit metalloproteases. Metalloproteases are the enzymes that chew your plaque, and yeah, so what? No, very important, because if you don't have enzymes that chew your plaque, then you don't have thrombosis. So not many people study that, but all the pathways related to extracellular matrix and to metalloproteases are very important, and I think we should study them more in the future. So 30 years of research on olive oil polyphenols, and we're still working on it, of course. So these are my own conclusions. So what do you think? Why? Why is olive oil healthy? No one knows why. No one knows why. Fatty acids? No, not really. Is it polyphenols? Yes, but why? Who knows? Antioxidants? Not really. Anti-inflammatory? Probably. Microbiota? Probably. But we're still working on it. So olive oil, for sure, better cardiovascular health. We know that from the pre-med, we know that from the cardio-prev, we know that from hundreds of biochemical studies, hundreds of animal studies. Probably anti-carcinogenic, probably neuroprotective. And we're still working on the mechanisms of action. We wasted many years chasing antioxidants, and now we need other kinds of studies. And my own conclusion is the one I said at on the radio here on Canal Sur yesterday. There's a strong link between the quality of what you eat and your health. So spend money for what you eat. This applies to extra virgin olive oil. It must be expensive, and it must be of high quality. Here in Jaén, I've been, I think the first time I was here, maybe 25 years ago, olive oil, horrible, very low quality, very low quality. Now, super good, excellent olive oil. So they increase the quality. Oh yes, but they also increase the price. Exactly. You want quality? You need to pay for it. How much did you spend for your cell phone? Lots of money, right? And you don't want to spend money on extra virgin olive oil? No. Do spend money. Look for the best fish you can find. Look for the best cheese you can find. Look for the best extra virgin olive oil you can find. Spend money on that, and then try to save anywhere else you can, right? And that's what I said at the radio on Canal Sur yesterday. And thank you so much again for inviting me here, and I hope to see you soon next year or in a couple of years again in Jaén or in the rest of the world. Thank you again for inviting me.
Well, our next speaker is Dr. Kishun. He's Associate Professor in the Department of Nutrition and Epidemiology at University of Harvard, and his primary research is focused on to examine biomarker risk factors on health, and he will talk us about that. Thank you.
Thank you very much, Doctor, for the very nice introduction. And I also want to thank Stephanie for inviting me to give this talk, and really enjoy the time being here. And the venue of this congress is fantastic. So let me start my presentation. So I first want to mention what the current USDA data guidelines say regarding oil. So very specifically mention, people should consider, including vegetable oils and oils in foods, such as, say, for the nuts. But if you read the section specific in the report regarding oil, they very specifically mention also olive oil. Correspondingly, there's a recommendation that you should keep your saturated fat intake less than 10% of calories starting at age 2. And there's really abundant evidence to support a statement that you should use a vegetable oil, including olive oil, and in replacement of animal fats. This is a meta-analysis summarized evidence comparing olive oils with other type of oil or animal fats. And very clearly, you can see here, it's a lot better than the animal fats. Here is a milk fat, and down there is a lard. But otherwise, very comparable in terms of the effects on LDL when you compare with other vegetable oils. For olive oil with higher contents of polyphenols, they seem to be very effective on also raising the good cholesterol, which is the HDL cholesterol. This is another meta-analysis. So it looks like something inside the olive oil. If it's high in polyphenol content, they may bring extra benefits. That's even more so for some clinical outcomes. This is meta-analysis summarize the evidence from observational studies up there, but also the only trial so far, the randomized trial on clinical outcomes. And as you clearly say, that olive oil is, of course, from observational studies, you observe inverse association, but you observe even stronger effects in the randomized trial. And when it comes to type 2 diabetes, you got similar impression there that, I need to mention that for the randomized trial, of course, as we know it, they use extra virgin olive oil. But for those observational studies, could be really mixture, regular olive oil or maybe extra virgin olive oil. But nonetheless, based on this meta-analysis, I think we can say some implication that, extra virgin olive oil, again, seems to be more beneficial than this potential mixture of regular oil plus extra virgin olive oil. And Francesco just gave a wonderful talk. I just skipped this slide. Basically says, polyphenol, extra virgin olive oil contain a lot of polyphenols. But if we consider Mediterranean diet, because at least in Spain and other Mediterranean regions, people wouldn't just consume extra virgin olive oil in isolation, but in the beautiful Mediterranean diet, as demonstrated in this picture. And sorry, can I go back this way? And I had some cup of coffee there, right, to just make my point. It wouldn't, I think, defy logic because people do drink coffee in this region. But if you consider this diet, this is a really beautiful polyphenol-rich diet. And polyphenol themselves from olive oil, but also from other healthy plant-based food items, really a big family. You can roughly classify them into those categories: phenolic acid, phenolic alcohol, olive oil, one of the contributors, lignans, again olive oil, extra olive oil is one of the contributors, and the flavonoid itself is a big family and still being there. And it's amazing, plants, they produce those polyphenols for a purpose, primarily for their own defense. So they use polyphenols to defeat pathogens, fungi, bacteria, pests. But for some reason, to humans, to mammals, to birds, I think they also function as antioxidant. They have anti-inflammatory, insulin sensitizing effects. So to some sense, the fruits, vegetables, and olives, they prefer to be consumed by humans or maybe birds, rather than consumed by pests, by fungi, by bacteria. So for people who do answer the call of those fruits, vegetables by eating a lot of them, and seem to be able to benefit from such a diet. For example, this meta-analysis summarized evidence again from observational study. For this case, it's a flavonoid, total flavonoid in the diet and type 2 diabetes risk, and you observe very consistent risk reduction in type 2 diabetes when people who consume a lot of flavonoids. This meta-analysis basically summarizes evidence comparing high versus low intake. And similar story, when you look at flavonoids with heart disease, you reach the same conclusion that there's a risk reduction. But for this meta-analysis, they also did a dose-response relationship meta-analysis. And as you can see, this is HT, this is stroke, this is total CVD, and there doesn't seem to be any threshold effect between the flavonoid intake and CVD risk. So we have really many excellent trials that look at intermediate outcomes, insulin resistance, inflammatory markers, so on and so forth. But this is the only trial so far that, according to my knowledge, I focus on the clinical outcome. This is a Cosmos trial. It is a randomized clinical trial. Sample size is really significant. They enrolled men and women free of CVD and recently diagnosed cancer at baseline. Average age is around 70. They use 2x2 factorial design, administer the coca flavanol, but also placebo. On top of that, they also randomize participants to receive multivitamins. And the median treatment period is 3.6 years. The coca flavanol is 500 milligram per day, including 80 milligram of ipicatechin. So this is their main study findings. For the composite outcome is major cardiovascular disease event, including CABG, non-fatal myocardial infarction, fatal events, and also stroke. They observe a significant risk reduction here, like 16% risk reduction for participants who consume this ipicatechin. And those are Kaplan-Meier curve. As you can see, the separation of these two lines usually start really after about 1.5 years of consuming the polyphenols. This is for the total CVD. This is for CVD death. And very interestingly, we don't know why for the same trial, the same supplementation of FEV1-3Os didn't seem to decrease the risk of developing type 2 diabetes. So my team in the past 10 years also did some work really in the field of polyphenols, but our focus is lignans, which is one of the categories in polyphenols. So we use data from nurses' health studies, nurses' health study 2 and health professional. Basically, very quickly, we assess the diet every 4 years. Over time, from our beginning, we need to update those numbers. The annual follow-up right now is 2020 or 2018. So with this very unique data and excellent data, we look at the associations between lignin consumption and cardiometabolic diseases in the cohorts from different angles. So this is just one slide to summarize some primary findings that we look at lignin intake assessed by using the food frequency questionnaire with some major cardiometabolic conditions. We found, for example, lignin intake associated with lower risk of developing coronary heart disease, published at JACC 2021. As you can see here, the meta-erythritol, this is total lignin, this is meta-erythritol, this is isolaric erythritol. Those three lignin variables associated with lower risk of developing coronary heart disease. But if you look at these two lignans, pinoretinol and this is alaric, there's seem to be non-linear risk reduction. This is for the risk of developing type 2 diabetes. Again, the total lignans, the cycle and the meta, they are associated with lower risk of developing type 2 diabetes, but not for the two other lignans. This is for CVD mortality among type 2 diabetes patients. Again, for this total lignans, meta, and the cycle, but not for the other two. But it's very interesting when we look at weight gain. Meta, of course, and the cycle, they are associated with less weight gain, but the other two are associated with even stronger less weight gain in our cohorts. So based on this data, I think it makes sense to conclude that we observe some largely consistent findings when it comes to total lignans, but when it comes to individual lignans, we observe some inconsistent findings because there were these two associated with Pino and Laric associated with more strong association with less weight gain, but they were not associated with type 2 diabetes, and there's a nonlinear association with heart disease. When it comes to flavonoids, I think the inconsistency, the individual flavonoids, the inconsistency becomes even more apparent. This is a very sizable study from the EPIC Interact project. As you can see, there's some inverse association for flavonoids, and I think there's FEV1-3Os also associated with lower risk of developing type 2 diabetes. But in our own cohorts, we primarily find it's anthocyanins This class of flavonoids associated with lower risk of developing type 2 diabetes, and there's a marginal risk reduction for flavon 3-Os, but not for other classes of flavonoids. But are we really surprised by the some inconsistency in the polyphenol research? I think we should not. This is some really beautiful reviews published largely at AGCN to make points that there are really truly numerous factors that can really influence the actual contents of polyphenols in fruits, vegetables. Sun exposure, ripeness of fruits, so on and so forth will determine the actual contents of polyphenol in plants. On top of that, there are really significant amount of measurement error in the food composition database, but also to the food frequency questionnaire, the recall bias, so on and so forth. On top of that, and there's quite some very good evidence to suggest that even if you give people the same amount of polyphenol, in this case, in the form of orange juice, you still observe very significant between individual heterogeneity in terms of response. Those are markers of polyphenols in orange, in citrus fruits, and you can see it's very much individualized, right, in terms of the response of plasma levels of those polyphenol metabolites. If you look at antolignans, which are metabolites from the human gut, when you consume lignans, you observe same pattern, very much individualized patterns. Even more so for isoflavone metabolites, for example, ECO, you observe really dramatic between individual variabilities in terms of the production of ECO, even if you give participants the same amount of isoflavones. But of course, for antolignans and for the isoflavone metabolites, we know microbiota can really play a significant role in the production of antolignans and isoflavones. In this research, they just incubate human fecal samples with the plant lignans or plant isoflavones. Then they observe the production of those, anthodiol here, antolactone, and ECO here, and ODMA there. This is ODMA, this is ECO. You observe really dramatic, very different capacity of individual people's fecal sample in terms of their capacity of producing those metabolites from their feces. As a matter of fact, most polyphenols are going to interact with human gut microbiota one way or the other, because we know that 5 to 10% of polyphenols really absorbed in small intestine. The majority of them push down to the colon, and chances are they interact with the human gut microbiome. So with so many modulators between the consumption of polyphenol to really the metabolites that can enter circulation, that you can really expect those metabolites to be biologically function, the only chance to understand polyphenols' health effects is through biomarkers. I think that's the logic there. So my group also did some research in that regard. So this is the first project we collaborate in collaboration with Van Dam, look at antolignans in urine samples with type 2 diabetes risk. When we pull antodiol and antolactone together, we observe a roughly linear dose-response relationship between antolignans in urine sample. Here I want to emphasize it's a spot urine sample. We will come back to that point with type 2 diabetes risk. Also using controls from the very same case study that I mentioned for the type 2 diabetes, we also observed that those two antolignans, antolactone, antodiol, is also associated with less weight gain among controls. How about the antolignan levels with coronary heart disease? We also published data 2021 at AGCN demonstrating that in the nurses' health study 2, which are younger women, we observed really significant risk reduction in terms of coronary heart disease. for antolactone in plasma samples. But for the man, the green triangle, you can see there is a risk reduction, but that's not significant. For other flavonoids, we observe really inconsistent findings. The only flavonoid marker that we found, inverse association is for this aspartame, which is polyphenol rich in citrus fruit. But for other flavonoids, there's no association right there. But again, we shouldn't be really surprised because we use spar urine to measure those flavonoid metabolites. And as you can see, they have if you use spar urine, you run into the risk of mirroring really short-term exposure to the flavonoid intake. This is one study we conducted, basically measured the same flavonoid compounds from 2 urine samples collected 1 to 2 years apart from the same individual. Then we calculate the intra-class correlation coefficients for the 2 assessments. As you can see, most of the flavonoid metabolites, they are very poorly reproducible over time. That means you cannot just use one single assessment of those flavonoids in spar urine sample to represent the long-term status. Only exception is the 2 antolignans and some caffeic acid and ferulic acid, those are phenolic acid. So given this, really poor reproducibility, I think the people, again, shouldn't be surprised that we largely observe no associations. But I think on the other hand, we are lucky that we're dealing with type 2 diabetes. So the question is, because it can reflect more recent diet, but because diabetes can also, if you push people from pre-diabetes to diabetes, that wouldn't take too much long time. So chances are that maybe we can observe some associations in the more recent follow-up, but not in the more remote follow-up. So that's precisely what we observed here. If we separate the follow-up in the middle to see like early follow-up here and versus later follow-up, we did observe an inverse association for the early follow-up. I just gave one example of flavonone, but also for caffeic acid, for a couple other flavonoid subclasses, we observe an inverse association for the more recent follow-up, but not in a remote follow-up. And the other point I want to make that, if you use 24-hour urine samples, look at the same experiment, that when we use 24-hour urine samples to assess reproducibility, that is significant improvement. You remember for the previous slide, most of the metabolites, their ICC is really at around 0.2 level, but for this new experiment, I think we managed to improve the ICC to close to 0.4. So that the point is, really for polyphenol research, I think, using blood sample is one thing. The other very valuable biospecimen that people should consider is 24-hour urine sample. It's challenging to collect, but it's going to be really valuable for polyphenol research and maybe for other type of molecules that with also poor reproducibility over time. So I'm going to use last couple of slides to demonstrate the role of microbiome in the association between polyphenol intake and the risk of metabolic health. So this is a very small study called the Man's Left Cell Validation Study. 307 men, we collected repeatedly 2 pairs of stool samples, blood samples, and also 2 pairs of 7-day diet records. So with this data, we able to answer the question whether microbiome may modulate the consumption of lignans and also the production of antolignans. So what we did is to look at microbial features that predict the plasma levels of antolactone. We found roughly 18 microbial species that 5 of them predict positively, and some of them, rest of them predict negatively the plasma antolactone levels. And then we use those microbial species to make a score. So the score represents the capacity of the microbiome to produce antolactone. for humans. So we observe, this is the primary finding we observe, very interesting. Look at the red line, those are people with higher microbial species score. When they have higher species score, we observe stronger positive association between lignin intake and antolactone levels in plasma. But for the green line, those are people with lower microbial species score. For those people, you still observe some positive association, but at a statistically weaker correlation between the intake and the antolactone levels. So this figure shows the same thing, that only people with higher intake but also higher microbial species score, they have exceptionally higher levels of antolactone in their plasma. And together, the microbial, the gut microbiome and the antolactone together can explain 50% of the association between total lignin intake and the metabolic health as assessed by HbA1c, so on and so forth, metabolic syndrome, essentially. So my conclusions, olive oil, especially extra virgin olive oil, has really clear cardiometabolic healthy benefits. And we think polyphenol contents in olive oil and other key plant-based components in a beautiful Mediterranean diet may play a really important role in at least partially accounting for the observed effects of Mediterranean diet on diabetes or cardiovascular disease risk. I think biomarkers of polyphenol intake are really crucial to consider in any research to really make the link between the intake and health outcomes, but there are challenges that shall be tackled, including the short the poor reproducibility, so on and so forth. So really by using new markers, new technologies, but also better biospecimens for the research. And lastly, the role of gut microbiome in the polyphenol research in the era of precision nutrition shall be fully elucidated. This is a really I think it's a good timing right now we are in the area of precision nutrition. I think when it comes to polyphenol research, this is a perfect case that people shall consider the role of gut microbiome in their research, so that they tailor the diet toward the individuals to hopefully to produce higher contents of bioactive compounds to benefit their health. All right, those are my primary collaborators. I must have missed many of them, but so far those are my collaborators, and I want to thank NIH for their grants, and I want to thank our participants for their dedication. Thank you very much.
Bueno, muchas gracias. Thank you very much for this interesting session. Well, I would like to ask if there is anyone in the room that would like to do any question or comment. Yes, please.
We're doing questions, correct?
Sorry?
Questions.
Yes.
So, Professor Visioli, I mean, both of you had an outstanding presentations. I would really like to point out that you found a decrease in the level of glutathione. You passed very fast the slide. Did you see an increase of GSSG at the same time?
No, both. They decreased both the reduced level, the levels of reduced and oxidized glutathione.
Both of them were reduced. Okay, and that was in the plasma?
That was in the plasma, and I really don't know why, because so a few years ago, no, many years ago now, I was in Malaysia, and we did a study, a short-term study, giving a supplement. Maybe that's the difference with 2 humans, and we saw an increase in glutathione. And everyone said, yeah, of course, polyphenols increase glutathione because they activate phase 2 enzymes. Okay, applause. Yeah, thank you, thank you. And now we see the other way around. Maybe it's the dose, maybe it's these are mice and the other ones were humans. Maybe I don't know.
Or I'll give you another explanation.
Yeah.
So we have developed models. My lab works on glutathione metabolism and synthesis and homeostasis. So we have created knockout mouse models, and we can discuss that a little bit more after this session. But what we have found is that mice that they have lower glutathione, they are more resistant to insulin resistant. They're lean mice. You put them on high-fat diet, nothing happens. You put them on dioxane treatment, nothing happens. You put them on alcohol, nothing happens. And they still have about 20 to 30% of the total glutathione compared to the wild-type mice. So what's the explanation? We published a paper a number of years ago that when you have a low glutathione, you have the phenomenon what we call hormesis. Okay. And what hormesis is, because of the constant oxidative stress, you have the upregulation of the antioxidant genes, and that protect from the insult.
Okay, very interesting. Thank you so much. Thank you.
Right.
See, there's always something to learn. Thank you. Thank you.
There is any other question or comment? Yes, please go.
A quick one. Congratulations, the presentation was very good. I have a question for Dr. Visioli. Your study, the preliminary, didn't publish yet. You didn't tell us what type of mice were there, the wild-type mice, and the age of those mice, and the gender.
Okay, yeah.
Because sometimes you can have difference in terms of when the age of the animal, the gender of the animal, so forth and so on.
Yeah, no, we did 50-50 male and females. The age, I think we took them when they were 6 months old, and they're not wild type. They are a particular strand that are prone to become obese, but the exact name of the strand I forgot now. My collaborator knows it. He's an expert on obesity. And so no, it's a particular kind of mice that people use when they study obesity. I can't remember exactly the name of it.
Okay, there is any other question? Yes, go ahead, Stefania.
First of all, thank you very much for these wonderful presentations. I have a question for Dr. Chisholm. You showed a slide in which the effect of the polyphenols was different in the nurses' health study too, and in the health professionals' study. There was a graph in which two studies were plotted. So there are two big differences. One cohort is of men, the other one is of women, but also the age range is different. So what do you think that may be the most likely explanation for the difference? Is it the sex of the participants, or is it that there's an important difference in the age, on the effect of the polyphenols depending on the age of the participants?
Yeah, I think that's really, really wonderful question. I think, if you, first of all, the gender difference, I think, as we know, lignans, isoflavones, they are also phytoestrogens. So there's naturally gonna be some gender-specific effects given that, men versus women, of course, estrogen, endogenous estrogen levels, estrogen receptor levels, so on and so forth, are different between men and women. Sometimes we do observe certain interactions between the postmenopausal status, postmenopausal hormone use, with isoflavone biomarkers or polyphenol, lignin biomarkers, with the association of type 2 diabetes, coronary heart disease. So I think that's true for a lot of polyphenols. When they have estrogenic effects, you would expect to observe some gender-specific effects. When it comes to age, for the Cosmos trial, that's an interesting case. As I mentioned, the average participant age is 70 for the Cosmos trial, and I demonstrate, for type 2 diabetes risk, there's no risk reduction, which is very surprising. given that, you demonstrate, the insulin sensitizing effects of polyphenol flavonoids. But for the Cosmo trial, they gave a very high dose of 500 microliter of coca extra. They didn't observe anything for type 2 diabetes risk. And I didn't show some research here that we just still working on the early revision at BMJ. We observed, dark chocolate intake actually has certain age-dependent effects. We only observe some inverse association between dark chocolate intake and the type 2 diabetes among younger participants, but not among older participants. We use age 70 as a cut point. We see really clear interaction. So our theory is perhaps, when you get older, the biology could be different, the weight change, the body mass index, so on, could be really different, so that you have better chance to observe health effects among younger individuals. But it's a complex question, so we hope to do some more research in the future to answer questions better. Thank you.
There is any other question? Well, I would like to ask both of you a question. Well, first to Francesco. Yes, you say that with polyphenols you eat less. I have read some papers that phenolics or extra virgin olive oil, you eat less. That seems that there is an implication in obesity, but I have never heard that you eat less. No, I thought that it was because it was increasing the metabolism or.
Yes, it's complicated. I was listening to Edward yesterday when he said that there is an whatever you eat less, an exogenic effect. Maybe you don't eat less. For sure, you activate mitochondria. We published the review last year with my collaborator, Tori Hagen from the Oregon State. These polyphenols do activate mitochondria. So maybe you burn more energy. That happens with green tea, for example. It has a thermogenic effect. You drink green tea and you lose weight. A little bit, not much. But why? Well, you absorb less fat because catechins in green tea, they bind to fat, and so you don't absorb as much fat. And also you have a thermogenic effect. So they all probably contribute. I don't know if you eat less, but you don't gain as much weight as with the same calories coming from other kinds of food.
Then I have a question for you about lignans, because, for example, in the Predimed, we have find that the consumption of lignans was related with less cardiovascular events, but in our case, the lignans were coming mainly from olive oil and olives. In your case, where are these lignans your nurse health study or health professional? Where are the lignans coming from? Cereals? Where is the main source of lignans in this population?
That's a really, really good question. I think let's put the cycle aside, just comment how original, Pinot and Lyric, they are largely, a lot of them from whole grain, some of them from vegetables. And, interestingly, I think if I remember correctly, Pinot Rational, some of them actually from also beer consumption. But, when you talk about cycle, that depends on whether you assess flaxseed or not. We see really dramatic increase of cycle intake at certain points during our follow-up when we add flaxseed into the question. When people say, okay, I use flaxseed as supplements, I just put flaxseed on top of my salad, their cycle consumption will increase dramatically. But for people who do not use flaxseed, the cycle is still from whole grains, those kind of other plant-based foods. But my point is that once even people consume a small amount of flaxseed, their cycle intake will increase very dramatically.
Okay. Well, I think with that we could end this session. Well, thank you very much to both the speakers. And there is now 10 minutes, I think, after 5 minutes after. So I think that we will go to the next session. Thank you.
Thank you.